I want to start off today talking about something new. That is oxidation-reduction reactions. Oxidation-reduction reactions are incredibly common in chemistry. A lot of what we do in chemistry has already been these redox reactions. And I should point out really quickly that chemists don't always call them by their formal name. Like oxidation reduction is a lot to say. We generally abbreviate it to just be redox. But these two things mean the same thing interchangeably. And so redox reactions underlie so much of what you've already learned. We've just not given it a name or talked about it yet because in the order of things, this stuff makes more sense late in the year than at the beginning. Okay, but that being said, redox reactions aren't so bad. They're just the kinds of reactions where electrons move between atoms. So in a redox reaction, we're physically taking the electrons from one thing and giving them to another. Something is giving up electrons and something's taking them. Not so unlike the balance between H and OH in an acid and a base. But here we're talking about electrons. And just to make sure you really get this point home, let's ask a quick question. Now, one thing I want you to notice is if a question answer is about protons, the odds are in this chapter that answer is wrong. This chapter is all about electrons and just moving them around. And the sooner you can kind of see, oh yeah, all I'm actually doing is moving electrons, the easier this is going to be. So today we're really focused on knowing how do I know where the electrons moved in a reaction. So let's take a look at one of the most famous reactions there is. That would be the reaction between elemental sodium and chlorine to make sodium chloride table salt. Now, technically the equation as I've written it here is a lie, right? Chlorine should be a diatomic, but let's make it as simple as possible. This reaction exists. It's a reaction between elemental halogen and elemental alkali metal, right? A very energetic, very reactive situation. As a matter of fact, this reaction exists in real life, so let's take a look at it on video. So this is a video taken from a YouTuber called Nal Red. You can see the two ingredients here, sodium and chlorine, two elements. And he's heating the sodium up in a little broken piece of test tube, and he's going to lower it into the chlorine gas, the gas with a greenish hint. You can see the reaction is very, very immediate and very energetic. There was not a lot of sodium, not too much chlorine, and yet this would go on for well more than a minute. It's a really pretty reaction to see, and one I'm not so comfortable carrying out myself. Obviously, this is a redox reaction because we're talking about it in our redox chapter. But you know something else about this reaction. It's an element and an element combining to make a compound. So that kind of reaction also is something you can give a name to. So what kind of reaction is that again? Kind of a quick review question. So this is a synthesis reaction, right? Synthesis reactions are incredibly common. And it's not to take away from the fact that this is synthesis, but it's also redox in addition to that. We'll come back to this reaction in a while and talk about how we know that the electron moves from the sodium to the chlorine and all of that. But for now, I just want to kind of keep it in the back of our mind that it exists. And let's make a couple really key definitions for today. Namely, that oxidation is the loss of an electron, right? When I oxidize, I lose electrons. And when I reduce, I gain them. Now, let's actually make sure you've got that. So a quick question should pop up. So reduction is gain. That's really confusing to me, actually. And the first time I learned this, I remember being really frustrated by that. Because after all, in English, reduce means to go down, and gain means to go up. And so how can reduction mean to gain? Why didn't we just call oxidation and reduction the opposite things? Then it would make perfect sense, right? And that makes pretty good sense. And even to today, I will mess myself up on this if I'm not thinking too much. But this makes sense if you remember one key fact. And that key fact is that electrons are negative, right? Look, in an atom, we have a nucleus comprised of lots of protons and neutrons tight together, right? They're all right there. And then a cloud around the outside, far away, are all the negative charges in the electrons. So if I add more of these minuses in here, then this atom is going to act like it's more negative. That is, it's going to reduce its overall number. Even though the number of electrons went up, the overall plus-minus balance is closer to minus now. In the same way, if I start taking away these electrons, these minus charges, right? It's going to leave behind a disproportionate number of pluses. That's going to make the overall charge rise. Or in this case, we're going to call that oxidation. And this does confuse me a little bit. But if I think about it like math, it helps some, right? Like if I have a number minus a minus number, I end up getting a bigger positive number, which can be a little weird. To take away a taken away number, right? To minus a minus is something that takes a while to learn. And this right here is what makes this chapter a little hard. Now, I think there's an easy way to remember this. Because frankly, remembering that oxidation is loss and reduction is gain, doesn't work for me that well. But there's a mnemonic. And that mnemonic is Leo the lion goes grr. So, if you lose electrons, you oxidize, and if you gain electrons, reduce. L-E-O-G-E-R, Leo says grr. And this works better for me. So this is going to help me remember what is oxidation and what is reduction. If I lose electrons, I'm going to call it oxidation. So for a while, I might even write this little phrase on your sheet and ask you what's actually going on. So, a quick question really quickly. Now, let's come back to that reaction we had earlier. The reaction of elemental sodium and elemental chlorine to make Na plus and Cl minus. Wait, NaCl, not Na plus Cl minus, right? But what's actually going on in this equation is that two things which originally didn't have pluses and minuses suddenly do. And that plus and minus are why things want to stick together, right? Just like a magnet, opposites attract. And in this case, what's actually going on is an electron from sodium is leaving and physically moving over to the chlorine, right? And so this one's losing a minus. That means its number's going up. It's being a plus. And this one's taking it in. So it's getting more of those minus charges and it becomes a minus. And it's this movement of electron from one element to another that actually lets this reaction happen. And all that energy and the bright yellow light you saw in the reaction, well, that's a result of just these little electrons moving from one element to another. Just one single electron per atom is enough to drive that whole electron forward. Now, it's really hard to think about this in real life. Right, I'd have to sit down and pause and think. And scientists came up with a shortcut so I don't always have to do things that way. And that is to use what are called oxidation numbers. And in an oxidation number, we're going to give it an assignment, which is the number of electrons gained or lost by an element in a reaction. And generally, in an oxidation number, you'll see oxidation numbers written above. So here, very quickly, I have NaCl, and then the Na is in a +1 oxidation state, and Cl is in a minus. So very quickly, I'm going to ask a quick question. So what I want you to see here is that these numbers change, like 0 to +1 and 0 to -1. They're what determine what happens in a chemical reaction. Now, you don't know how to find these numbers just yet, although a lot of you probably see, oh yeah, Mr. Eric, those are just ion charges. Well, they are most of the time, but not always. But the fact is that moving this electron made one thing a plus and one thing a minus, and this way of writing numbers out makes it easier. Actually, there's one thing that makes it even easier. And that's connecting the different elements with a line. So for instance, oxygen and oxygen are connected in this reaction, and so is magnesium. And that's something worth noticing. These lines here connecting the two pieces are very common to redox. And so they will always be the same element. And again, I don't care how I'm getting these numbers up top now. That's a different lesson. Right now, I just want you to notice that oxygen went from 0 to -2. So a question, what happened to magnesium? So one of the things here that's interesting is this actually tells us a lot more about it, right? For magnesium to go from 0 to +2, it had to lose electrons, right? It had to drop electrons away, right? It had to give them to something else. In other words, for this particular thing, I had to lose electrons. And I didn't just lose one, I lost 2. So I could say this lost 2 electrons. And that means, of course, that up here something else had to happen, right? And I went from 0 to -2. So what did happen there? right? Because if I'm losing electrons here, they have to be given to the other thing. They can't just be created or destroyed. Now, remember, we had a name for this. We said that oxidation is the loss of electrons, and reduction is the gain of electrons. So, apparently, in this reaction, magnesium was oxidized, and oxygen was, well, reduced. Right? That the gain of electrons caused reduction, and magnesium had oxidation happen to it. But this lets us come up with a shortcut, right? If these two things are true, which they are, oopsies, well then I can have a new thing. Whoop. Which is, in an oxidation, the number goes up, and in a reduction, the number goes down. And finally, something that actually makes sense, right? Let's actually check in really fast, right? Let's look at another reaction, or a real reaction. A reaction which is so absolutely insane that I don't know if it's ever been done. Cesium and fluorine. This is insane because both these things are incredibly reactive. And right now I want you to take a look at cesium, which went from 0 to +1. And I want you to tell me if that was oxidized or reduced. So cesium was oxidized, and that's because the number went up, right? 0 to +1. And by extension, 0 to -1 means that fluorine was reduced. And you're going to notice that oxidation and reduction always come in pairs. This will never be oxidized and this oxidized, and this will never be just reduced and this won't be anything. You will always see one thing being oxidized and another being reduced. And that makes sense when you think about it in terms of the electron, right? This cesium had an electron. It was perfectly balanced. And then it gave it up to fluorine. When that happened, this thing's missing a minus, and this thing's got a new minus. So this thing's charge went up, and this one went down. This one was oxidized, the cesium was oxidized, and the fluorine was reduced. And because the electron is physically being moved, that's why these things have to come in partners. Now, most of the questions I'm going to ask you for the next day are just going to be like this, where I give you a chemical reaction, and I give you some of the oxidation numbers. Again, you don't need to know how to find these yet. And you're going to tell me, hey, was this oxidized or was this reduced? Now, I did do a little Googling, and someone actually carried this reaction out in England. And because it's so incredibly strange, cesium is extremely hard to get your hands on. Fluorine is extremely dangerous. And the fact that someone got both of them in the same place and said, hey, let's react them is too cool. Let's take a look at that reaction before we go on.
And this is Professor Eric Hope here from the University of Leicester. So thank you very much for helping me out with this. What was your first reaction, by the way, when I said I want to try cesium with fluorine?
I thought you were totally and utterly mad.
This is my cesium. Have you seen cesium before?
No.
Not quite this. There's quite a lot of it, isn't there? It's quite beautiful.
Beautiful, yes.
And so dangerous. So this is a combination between the two most reactive elements in the periodic table. Incredibly beautiful reaction there between cesium and fluorine, this intense light, and I don't think many people have seen that before.
Alright, so let's look at one of the most familiar reactions there is, and that's the reaction with elemental iron and elemental oxygen. That is the rusting reaction. And I want you to tell me which chemical here, the Fe or the O2, which one of these things was reduced? Which thing ultimately took the electrons in this reaction? So there's a question for you up top. As you can see, oxygen went from 0 to -2. So that was a reduction reaction, right? The number went down. That means this one took the electrons and this one gave the electrons up. Now you might notice the number of electrons moved here isn't equal. That iron apparently gave up 3 and oxygen only took 2. And that's because these are each individual atom within this larger compound. If I look at +3 times 2, I get +6, and -2 times 3, I get -6. And again, that's why I'm giving you these numbers for now. So for now, the fact that these things don't equal up is okay. All right, let's do one more of these and make sure you've actually got this down. It's a really weird reaction. Let's burn sodium metal, right? The thing you throw it in water and explodes in oxygen. And before we even worry about the reaction as it happens, let's take a look at it in real life, because this is one of my favorite confusing things. So here you can see a chunk of sodium metal, and it's being heated with a Bunsen burner. And it melts really fast, and you can see that gray oxide layer on the outside. And we speed things up here, and you can see it burns till it's got a black skin. And in chemistry, I actually would expect that black skin to stick around, but that's not what happens here. Instead, it catches itself on fire, and it burns in this weird forest-looking way that slowly cools off to make a yellow chemical. And that yellow chemical looks really strange to me. It doesn't look like I would have expected from a burning metal. But hey, here we are. All right, so I want to know where this +1 came from. How did sodium get to a +1? Because that's the thing in this chapter we're trying to understand first. All right, so sodium had to lose an electron, right? Because it got more plus, which means, of course, oxygen took it. Now, those who are best at chemistry might notice this isn't what I think would form, right? Shouldn't it just be Na2O? Shouldn't it be sodium oxide? And that's what's so confusing about this reaction, because it actually makes sodium peroxide, which is a super weird chemical. And we get back to Rockhurst. I want to show it to you because it's really neat. If you put it on a piece of paper, it sets it on fire. For tonight, you don't have any new homework. For tomorrow, you're going to do a worksheet via Google Classroom asking you to look at sodium, oxygen, and other elements like it and tell me, hey, in this reaction, did it gain electrons, lose electrons? Was it when it gained electrons reduced? When it lost electrons, was it oxidized? Talking through what actually happens in a chemical reaction using these kinds of notes. I want to thank you for playing along with this new kind of learning. I know we still have a long way to go, but hopefully this helps. Until I see you again in a couple days here in this forum, good luck, and all your homework will be posted to both Google Classroom and my homework over the next couple days. So for now, again, be gentle to each other, and I'll see you soon. Buen camino en todo.